In the last lecture we have discussed application of CFSC and factors affecting CFSC. In this particular video we will be solving the questions based on the topics that have been discussed till now. The very first question, it is from GATE 2012. The question is the magnetic moment of a cobalt complex in which you can see a cobalt is being in a +3 oxidation state is 5 Bohr magneton. The total stabilization energy will be. So here actually we are supposed to find out the CFSC for cobalt +3. Actually before going ahead with the video, you must note some of the points, and those points are: if suppose your central metal ion, if that central metal ion is being in an oxidation state greater than +3, always remember that complex is going to be a low spin complex. Then if suppose a central metal ion belongs to 4D series or 5D series, again it will always make a low spin complex. Then if suppose the cobalt is being in the +3 oxidation state, cobalt in +3 oxidation state will always be low spin except halides, then in case of sulfide and with thiocyanate ion. Then CO+2 will always be high spin except some of the except when it is being in a very strong field ligand like carbonyl. But here in this case you can see this is cobalt +3. As I said, cobalt +3 will always be low spin. But except halide, sulfide and thiocyanate, you can see that here the cobalt +3 is being with halide. It means it is going to behave like a high spin. This complex is going to be high spin complex. So the thing is, as I have discussed in the last video, that for high spin complexes, when we are calculating CFSC, we don't take into account the pairing energy. And you can see from the options are like 0.4 delta O, this is 0.4 delta O plus P, 0.24 delta O plus 3P and 1.8 delta O plus 3P. As I said that this complex is going to be a high spin complex, since CO plus 3 is going to be it is with halide. So the thing is that it is not going to have any pairing energy. So all the three options over here have got pairing energy, so they have to be cancelled. So undoubtedly the correct answer is going to be this, but still we will solve. So now since this is cobalt +3, so cobalt +3 means what it is going to, it is D6. So since high spin 1, 2, 3, 4, 5 and 6, so this is going to be 0.4 into 4 delta O plus this is 0.6 into 2 delta O. 1.6. So the answer is going to be 0.4 delta O without pairing energy, and hence option A is going to be correct. Now the next question. Is from this question had come in CSIR-NET June 2013. The question is the delta T, that the delta T of the following complexes follows the order. You can see here all the three complexes are of cobalt complex. In this particular case, the cobalt has got +2 oxidation state. Here also the cobalt has got +2, and here also the cobalt has got +2. So in all the three cases, cobalt is belonging to +2, and cobalt has got +2, and as I said, cobalt +2 will always be high spin. So it is going to have how many electron? D7 electron. So actually the CFSC, if we calculate by this particular method, it will give the same value. But the thing is that this question should be solved on the basis of the strength of ligand. I have discussed the factors affecting delta value in the last video, that higher the strength of ligand, higher will be the delta value actually. So the thing is that if you compare the strength of ligands, here the ligand is chloride, here the ligand is bromide, and here the ligand is isothiocyanate. So undoubtedly if we compare the strength according to the spectrochemical series, this is going to have the highest strength. Then this will have the lower than that, and this is going to have the least amount of strength. So this is the most weak field, I would say, in comparison with all of them. So this that is C is going to have the highest delta T value. C is going to have the highest delta T value, then A and then B, and hence option number A will be correct. The next question had come in GATE 2016. the magnitude of difference in the crystal field stabilization energy difference in CFSE values in octahedral complexes, ignoring the pairing energy of FeH2O6 2 plus and FeCN6 4 minus. Here if you check in this in these two questions, the complexes are in both the cases. If you compare, here also Fe is in the +2 state, here also Fe is in +2 state. So +2 state means it is going to have D6 configuration, here also it is going to have D6 configuration. So they are differing in terms of the ligands which are attached to them. H2O is a weak field ligand and Cn minus a strong field ligand. So this is going to be high spin complex, this is going to be a low spin complex. So let us find out their CFSC. For this one, so this is high spin, so 1, 2, 3, 4, 5 and 6, and for this is a low spin, Cn minus is a very strong field again, 1, 2, 3, 4, 5 and 6. Now if you calculate over here how much it is going to be, this is 1.6, this is my 1.6 minus 1.2, so it is going to be 0.4, and if you check over here how much it is going to be, this is 2.4, and what they are asking us the difference between two. So 2.4, if we take the magnitude, 2.4 minus 0.4, so it is going to be 0.2. The answer for this question is going to be the answer for this question is going to be 2.0, that is 2.4 minus 0.4, that is 2.0. And here for this question the options were not given, and so this is how this particular question is to be solved. This is from GATE 2016. Now the next two questions are on the basis of Werner's theory. A compound has empirical formula COCl6 5 ammonia molecules. The ligands are actually 5 ammonia molecules and Cl3. We just have to guess on the basis of the information given that which are the ligands being in the coordination pair and which are the ligands that are being in the ionization pair. And always remember, the ligands which are being or rather I would say the ions which are being in the ionization pair are the free ones, and they can if suppose we are adding AgNO3 to it, then they are able to form PPT with it. So the thing is that what is given in the question, a compound has empirical formula COCl3 5NH3 when aqueous solution of this compound is mixed with excess of silver nitrate, 2 moles of AgCl PPT per mole of compound is formed. On reaction with excess of HCl, there is no ammonium ion detected. What does that mean? On reaction with HCl, no ammonium ion detected means in the ionization pair there isn't going to be any ammonia molecule. So the thing is that if you see in any of the options, if there is any ammonia molecule in the ionization pair, you have to cut those options. Next, what is the most important information given? That it is forming 2 moles of AgCl PPT. 2 moles of AgCl PPT means it must have chloride ions, 2 chloride ions in the ionization pair. So the thing is that the only option with the 2 chloride ion in the ionization pair is nothing but option A, and this is how the question has to be solved. Next one, a solution containing 2.674 gram of COCl3 6 NH3 was passed through a cation exchanger. The eluted solution gave 4.305 gram of silver chloride with AgNO3 solution. The another complex formed with AgCl is. Now the thing is that here this question is not as simple as this question, because here in this particular question we have not been given the number of moles of AgCl that is a silver chloride form. If suppose we have been given number of moles, like in this particular question we have been given number of moles of AgCl, so we can easily tell that 2 chloride ion must be in the ionization pair and the question can be easily tackled. But here we have not been given the number of moles of AgCl form, but so we have to find it out. So let us see how to find it out. So here what it is saying, that COCl, a compound which has got empirical formula COCl3 ammonia molecules. So it is, when it is passed through a cation exchanger, it forms solution A. Let's say it forms solution A when it is passed through a cation exchanger, and now this solution A, when it is treated with the solution A, when it is the thing is that a solution containing this was passed through a cation exchanger, the eluted solution gave 4.305 gram of ppt of silver chloride when it is treated with AgNO3 solution. When it is treated with AgNO3 solution, it is giving solution B, and along with that it is giving AgCl, ppt of AgCl. So initially how much gram of the reactant is COCl3 6NH3 present? It was 2.674 gram, and in the end when the eluted solution was treated with AgNO3, it has given 4.305 gram of AgCl. So the thing is that we know this is a very basic formula, and we are supposed to find out this B, not this A. We are supposed to find out B. So the thing is that we know how to find out moles from when the weight is given. So just divide this particular this gram quantity by the molar mass, and we are going to get number of moles. And if you divide this by the number of moles of, if you divided this by molar mass, you will get 0.01 mole of the reactant, and if you divide this by its molar mass, you are going to get 0.03 moles of AgCl. So here what does that mean? If 0.01 mole of the complex is giving 0.03 moles of AgCl, it means 1 mole of this complex will give 3 mole of AgCl. So here in this way we have actually found out the moles of AgCl. So moles of AgCl, which means in the reactant there has to be 3 Cl, that is Cl minus or the chloride ions in the ionization sphere. So the thing is that 3 chloride ion in the ionization sphere means the complex should have been this one, but this is not B, this is actually A. We have been asked the another complex form with AgCl. We are supposed to find this one. So the thing is that the eluted complex, actually the reactant has got 3 chloride ions in the ionization sphere. So the reactant actually is this, that is CONH3. And now when it is going to be treated with AgNO3, the B solution that we are going to get, the 3 chloride ions are going to react with AgNO3, and we will get 3 moles of AgCl, and these 3 chloride ions will be substituted by this NO3. So it is going to be CONH3 6, and in place of this we will get 3 moles. So the option is going to be, the correct option is going to be B. That is about the questions on the Werner's theory. Now next we will discuss questions on electroneutrality principle. So the next question is about electroneutrality principle. So let me revise. So according to electroneutrality principle, those complexes in which the metal, the central metal atom is attached to the ligands which are higher in electronegativity will be stable, and then like the thing is that the metal has to get rid of the accumulated negative charges on it, right? So the metal can do so by the one of the method is keeping its coordination number low. The second method is if suppose it is attached to the highly electronegative elements, then the third way, that if it is able to make back bonding with some of the ligands, that is if suppose the ligands are pi acceptor ligand. And the fourth way, if suppose the metal is being in a higher oxidation state, so the higher the oxidation state, more electron deficient it will be, so it will be able to take more number of electrons which are donated by the ligands, and more will be stability. So this was a part of revision. Now let us discuss the questions based on it. So the first question is, which of the following do not exist on the basis of electroneutrality principle? And one of the application of electroneutrality principle was, it tells whether a given coordination complex will exist or it won't. So the thing is that here we have been given a nickel chloride complex in which the nickel is being in the +2 oxidation state. Here if you see, here also the nickel is being in the here also it is going to be in the here the nickel actually is in the +4 oxidation state. Here the nickel is going to be in the +2 oxidation state. Here it is going to be in, like it is going to have, the metal is going to have lots of negative charge because this is a neutral ligand actually. So it is going to have a like 4 minus, there is lots of negative charge on this particular complex in case of this particular complex. And then if you check over here, the cobalt is going to be in the +3 oxidation state. Now, so if you compare, all three of them have got plus oxidation state, and here in case of this particular complex, the metal is going to have like lots of accumulation of negative charge on it, so it is going to be a very unstable complex, and hence according to electroneutrality principle, C is going to be a complex which has got the least probability of existence. Then the next one is correct order of stability of complexes according to electroneutrality principle is. Now if you check which have been the three complexes given, we have been given complex like Be, the beryllium complex in the +2 state. The second complex is given in, this is an octahedral complex given when B is in the +2 state. Then the other complex given is a tetrahedral complex where the coordination number is 4 and it is being in the +2 oxidation state. The third one is, it is with ammonia, and here also it is a 4 coordinated complex. So we know the complex in which the metal has got a lower coordination number will be more stable. Now if you check among these three, this has got a coordination number of 6, this has got this particular complex has got a coordination number of 4, this has got a coordination number of 4. So these two are undoubtedly going to be more stable than this particular complex. So the least stable should be the 6 coordinated complex. So among the options, if you check, the 6 coordinated complex being the least stable is the option B and option C. So other two can be cancelled actually. So now if you check in case of option and then if you compare these two, out of, now this is also 4 coordinated, this is also 4 coordinated, and this is also +2, this is also +2. So the stability should be checked on the basis of the ligand which is attached to the metal. And if you check here, the donor atom is oxygen, here the donor atom is nitrogen, and oxygen is more electronegative than nitrogen. It is able to pull the electrons from the metal to more extent than the nitrogen of ammonia. So undoubtedly this will be more stable than this, and the only option which stated is this one, that is option number D, in which the 4 coordinated complex having water molecule is the most stable. So option number D is correct. So this was about the questions based on the topics that have been discussed till now, and in the next particular video we will discuss the application of CFSC. That's it. Thank you. If you would have liked this video, like, comment, share, subscribe, and don't forget to